At the College of Engineering at the University of Nevada, Reno, we want to give you a brief look into some of the amazing work done by our student researchers in our nanofabrication laboratory. This is how we create a microchip in the Davidson Foundation Cleanroom. We start by first suiting up head to toe in equipment to prevent us from contaminating the lab. This allows us to achieve a very low concentration of airborne particles in our lab space, which is extremely important for the delicate work being done in order to produce the chips you see in all of our modern electronics. Even the smallest amount of dust or fiber can be capable of causing unpredictable results and ruin the microchips. Now, most microchips start as a simple silicon wafer. We load these wafers into a machine called a sputterer. Here, we'll deposit a thin layer of metal on top of our wafer. We load the wafer into a plasma chamber using a long arm that you can see on the machine. We then pump the air out of the machine in order to achieve a super low pressure, a crucial step in forming plasma. We'll use the plasma ions to bring atoms from the target metal onto the wafer. Now we'll take our wafers to the lithography room. We use the specific lighting in this space to better control the way light will interact with our wafers. Our work in this room begins with us applying a photoresistive material coating to the outer layer. This layer is important as it helps us protect the areas of the wafer we don't want being damaged later on when we get to the etching part of our design. Here we can see as one of our researchers prepares our wafer for the design process by cleaning it with acetone, isopropyl alcohol, and deionized water. Afterwards, we apply a primer and put it in the spin coater for an even coating, and then bake it at a high temperature. We do the same for our photoresist, which changes the color of the wafer. We put the wafer in our thin film analyzer, a different machine that will measure the thickness of our photoresist in order to ensure it's the right size. That layer will be just 1 micrometer, so it's important to be precise as this may affect how deep the etching is going to be on the surface. On this monitor, we can see what our design is going to be. In our lab, we use common industry software to design our structures. You can design circuits, structures, and even art. After finalizing the design, we move the wafer to this maskless aligner, which will place the pattern from our software directly onto the wafer. After a quick post-exposure bake, we get to develop the wafer. Look how quickly we can see that pattern appear after we place it in the developing solution. We make our way to this new machine called a plasma etcher. We use this to etch and remove material from the wafer both chemically and physically. There are many different parameters on the plasma etcher that you can control in this very complicated process. Our next stop will take us to the barrel asher, a device that we use to clean away any organic or unwanted materials from the wafers. Think things along the lines of dirt, dust, and skin. It also clears away all the remaining photoresist from our wafer. From there, we can use our stylus profilometer to measure and analyze the surface topography of our wafers and the designs in them. We can do things like capture the step height that we get when we add a new layer of metal on top of our silicon wafer, or see how rough or flat the surface of the wafer truly is. Throughout the fabrication process, we regularly inspect our wafers under optical microscopes, allowing us to catch any patterns or development errors early. Quality control at every step is critical when you're working at this scale. With the fabrication process complete, we can move on to dicing. Here, the wafer is carefully cut into individual pieces called dies. Each die represents a single chip. While the wafer shown here doesn't contain functional electronics, production wafers are diced with specialized machines to protect the delicate structures. To put the scale into perspective, take a look at this finished integrated circuit under a microscope. While the exterior package, the part with all the pins, is large enough to handle, the actual chip inside is incredibly small. That tiny rectangle at the center contains all the complexity and engineering that makes modern electronics possible. To inspect our work at the smallest of scales, we move on to one of our more powerful tools, the Scanning Electron Microscope, or SEM. At the nanoscale, traditional light microscopes simply aren't enough to view all the necessary details of the etched design. The wavelength of light is simply too large to do it. Instead, SEMs use electrons to generate incredibly detailed images of our structures. These images aren't seen directly, but are computed from data, allowing us to study features that are thousands of times smaller than the width of a human hair. From a plain silicone wafer to a functional microchip, every step of this process demands creativity and collaboration. In the Davidson Foundation Cleanroom at the University of Nevada, Reno, our students don't just learn how microchips are made, they make them. For more information on how you can become involved with the research happening here at the College of Engineering, you can visit our website.